In this video, I will talk about panel data models in Stata. Before you watch this video, please make sure you have watched my other video called Panel Data Models. I have opened up the Stata program here, and I already executed it, and this is the output here. So you need to download the program and download the data file and put the data file in the path of where Stata can read it. And let's begin. So as I said, we will talk about panel data models, and in particular, we'll talk about the pooled OLS estimator, the between estimator, the first differences estimator. Then we will compare the fixed effects within estimator, the dummy variable regression, the random effects estimator, and then we will finish with the Hausman test for fixed versus random effects. So we would be using data on training grants and firm scrap rate. So here we are creating a data directory and then we are reading in the data. We would be dropping the missing observations for the dependent variable. This is just so that we have uh, non-missing observations for the dependent variables. So let's go ahead, describe the variables that we will be using in the models, list the first 9 observations, so listing all of these, the first 9 observations, and then summarizing all of them. So this is how the data would look like. F code would be the firm code number. So this is data for firms, and this will be the code for the firm. Year would be one of these 3 years that we have the data. So we have a panel data. Log of the scrap rate is basically what's the scrap rate for the firm. So that's basically indicating productivity or lack of productivity. Uh, Total hours of training to improve this productivity. And here we would have dummy variables if the year is 88 or a year is 89. Grant would be equal to 1 if the firm received a grant, and grant underscore 1 would be lagged grant. So basically, has the firm received the grant in the previous year? So if we list the first 9 observations of all of these variables, this is what we're going to see. So here we have data for the first 3 firms, for the first firm, for the second firm, and for the third firm. And for each firm, we have 3 years of data. So now we have 3 firms with 3 years of data for each. And these are the scrap rates. This is going to be the dependent variable. Notice that scrap rates are somewhat lower for the first firm and kind of in the middle for the second firm and higher for the third firm. These are the total number of training and dummy variable for each of the years. So notice that here dummy variable for 88 is equal to 1 if year is 88. And this one is equal to 1 if year is 89. And this is whether the firm has received grants this year and in the previous year, and for the first 3 firms, they have not received grants. But if you look in the data, there are ones for some of the other firms. If we want to summarize the data, here's what we have. Of course, firm code doesn't make sense to calculate an average. Same with year, we have the 3 years. This is the average log of scrap rate and so forth for each of these variables. So how do we set the data as panel data? We use the command stset, and then we always put first in the I dimension, the cross-sectional dimension of the data, and then we put the T dimension, which is the time series dimension, which for us is year. So this is how Stata knows that we are dealing with panel data. So xtset f code and year, and it says the panel variable f code is strongly balanced, which means same number of years for each of the firms. And this is the time period for in years. Delta is 1 unit change between them. So if we summarize the F code, this is the code for the first year, this for the first firm, this is the code for the second firm, and this is the code for the last firm. And these are the years that we have. And so we have 54 firms, n equals 54, and we have 3 years of data. And here we see that we have strong balanced panel data where each of the firms has 3 years of data. Okay, if we want to summarize the data using the panel data command for summarizing, we will be using xtsum for summarizing, and we would be listing all the variables that we want to summarize. So now, these are all of the variables that we have here, and these are the means that we have above. Those means are the same. However, now we have overall, between, and within variation. So if we're to review what the overall, between, and within variation is, within is how does the each variable vary within the same firm over time. Between variation is how does one firm's data vary from the rest of the firms. That's between the firms. And overall is like how does the value differ from the overall mean. So notice how the standard deviation here for the F code is all of it is for the between variation and there's nothing for the within. Why? Because the firm code does not differ within the firm. Obviously, it's the same firm code, but it differs between one firm to the next. So that's why all the variation is here. Year, on the other hand, does not differ between the firms because it's the same year for every firm, but it differs very strongly within the year variable. So here we have a variable that all of the variation is within. So this is just to illustrate these different variations. The one case versus another, obviously this is how we set up the data as panel. We would not be using these variables within our models. These are the variables that we're going to be using in our model. So notice here that the between variation is about 3 times as large as the within variation. So what we're concluding here, the scrap rates vary 3 times as much between the firms as like within the firm. So it's there's more variation here between the firms than within a firm. On the other hand, if we see a variable like total hours, the between variation between the firms and within a firm is just about the same. So the same variation between firms and within firms. So here's these other variables. Obviously, the dummy variables for time only have within variation over time, not between variation. And for grants, we have a bit more variation within a firm than between firms. So this is a little bit of extra information that we have if we want to summarize data as panel data. Okay, so now let's go ahead and estimate the pooled or less, between, and first differences estimator. So for the pooled OLS estimator, we're just running a regression with LSCRAP being our dependent variable and all these other variables as independent variables. So here we're basically ignoring the panel data nature of our data set, and we're just estimating an OLS regression. That's why we're calling it a pooled OLS estimator, because we're pulling across between the firms and over time. And so this is the regression that we estimate here. And we're noticing that none of the coefficients are significantly different from 0 except for the intercept. So here, if we want to interpret a coefficient, this will be how the total hours of training across the firms and over time influence the log of scrap rate. So we don't distinguish between the variation. It's between the across the firms and over time. we see that this effect here is not being significant. So for the between estimator, what we are doing is we will be using the XTREG. So XTREG tells data to run, and this comma B calls the between estimator. So here Stata would be running the between estimator, and XTREG is the regression, but the panel data regression that it's going to be doing. So even though it looks like almost like the model here, the way we actually call these variables, and when we look at the between estimator, the regression output looks like as if this is like our original variables here. It's not the original variable, but it's the average of L scrap uh, over time for each firm. So here we have L scrap bar I. So this is the, again, average of the scrap rate for each firm over time. And these independent variables have the same transformation. So instead of the variable, this is the variable minus its average for the firm over time. This is why some of the variables have to be omitted because of collinearity issues. So here, how we would interpret these coefficients is that if total hours for each additional total hour from that a firm has invested in training more than other firms, how would that affect log scrap rate? But this coefficient here is not significant. But the between regression would show the variation from one firm to the next. And so this would be just that kind of variation. So we are basically eliminating any of the within variation over time because we are essentially collapsing the data set into one observation per year for each firm. So notice here that R squared would also get distinguished between within, between, and overall. And here we see that between the R squared it has the highest number because we're explaining most of the between variation, obviously, because it's a between estimator, and we're not explaining pretty much any of the within variation here. So now, if we want to do the first differences estimator, let's first take the first differences. So we're going to be sorting by F code and year. And then we're going to be generating the difference in the log scrap, total hours, and grant by doing d dot L scrap. So what the d dot operator does here is that it takes L scrap for the current year minus the L scrap for the previous year. And so that the d dot is the first difference operator that creates a variable that's a difference from this year minus the previous year. And so now now that we have these variables generated, the first differences estimator would have the difference in the dependent variable, the difference in the independent variables. Notice that we cannot include the other independent variables because when we are taking a difference from the previous year, they would be basically uh, they would be collinear, particularly for the time dummies that we have here. Okay, so here we have the first differences estimator, and uh, uh, we would be looking at this coefficient. So the way we would interpret this coefficient here is that if the total hours of training increase from one period to the next for a particular firm, how would the scrap rates change from one period to the next for the same firm? So this effect, though, here is not significantly different from zero, but that's how we would interpret it, is the difference from one year to the next. Okay, moving on, the next estimator that we would consider is the fixed effects within estimator. And how we would do the fixed effects within estimator is doing xtreg, putting the dependent variable, all of the independent variables, comma FE. FE would be giving the fixed effects estimator. So notice how here BE was the between estimator. Here's the fixed effects estimator. So this is how this regression output would look like. And here we have, here we would have these variables here. So for the fixed effects within estimator, we don't actually have the original variables. What we have is the within transformation, which means here we have log of scrap minus the average of the log of the scrap for each individual, for each firm over time. So we have the time demeaned variable. Again, each variable minus its mean over time for the same firm. And same with all of the independent variables here. All of them are demeaned like that. A variable minus its mean over time. So this is how we have here these coefficients. This coefficient is also not significant. So, but here the way we would interpret this effect is for each additional hours in training for a firm that is above its average, we would basically have what is the effect on the log of scrap rates that would be also above the average. So here that transformation is the total hours of training higher than the average. So again, this effect is not significant here. Notice that for the fixed effects within regression, notice how the R square is much higher than the between. The within R square is much higher than the between R square because this is the kind of variation that we're explaining here, the within variation. So notice and remember this number 0.22. So 22, we can explain 22% of the within variation that we have here with this model. Um, so after we are able to estimate this uh, this model, what we will be doing is we will try to recover the individual specific effects AI. So Stata actually denotes these individual specific effects as U. So how we're going to recover it, we would be using predict. We would call this AI, comma U would be calling these individual specific effects here. And so here we would be listing again the F code year, the dependent variable, and let's look into the first few numbers for these individual specific effects. And so this is how these individual specific effects would look like. So for the first firm, we have, these are the log of scrap rates. This is just the data that we had before, but these are the individual specific effects that got recovered afterward. This is the individual specific effect for the second firm, and that's the individual specific effect for the third one. So notice that the way we would interpret these individual specific effects is that there's something about the first firm that the log of scrap rates are that much lower than the average firm. For the second firm, they're 0.45 higher than the average. The log of scrap rates are 0.45 higher than the average firm. And for the third one, these log of scrap rates are 1.29 higher than the average firm. So these individual specific effects are unobserved factors. They're showing that there's something about that firm that has higher or lower scrap rates without explaining what exactly. If we summarize this AI, we can see that the mean is practically zero, and that is by design. The individual specific effects sum up to zero in the within estimation. Next, let's look at dummy variables regression. So basically, that would be an equivalent way to the fixed effects within estimator. Okay, so in order to do the dummy variables regression, we are first going to sort by F code, the firm code, and then we would be creating dummy variables, one for each firm. So I dot F code. Basically what it does is I dot F code would create 54 dummy variables, one for each firm. So here, the I.F code would be a dummy variable equal to 1 for the first firm. If it's the first firm, 0 for everybody else. The dummy variable for the second firm would be equal to 1 if it's the second firm, 0 for everyone else. And up until the last firm, which again would have a dummy variable equal to 1 if it's that firm, and 0 for any other firm. So this is what this I of F code is doing. And this, we're running a regression with all of the dependent variable and the other independent variables here. So this is how this regression looks like. So here we have the dependent variable, all the independent variables. These are the coefficients. And if you notice, actually, these coefficients here, if you scroll back up, these are exactly the same coefficients here on the independent variables as these coefficients here for the within or the fixed effects estimator. So let's see. So they're the same as the coefficients that we have here. Exactly the same coefficients. So this is actually by design how these fixed effects are done. But now we also have the coefficients on each of these dummy variables. So notice that the first coefficient here is normalized to 0 for the first firm. So actually this is the second firm, and that's a dummy variable for the second firm, and that's the coefficient. This is the dummy variable for the third firm, that's the coefficient, and so forth. So now we have, because we have 54 firms, we have 53 coefficients that are being estimated here, and then we have the intercept. Okay, so now these coefficients actually also happen to be individual specific effects. However, here the individual specific effect for the first firm got normal, the coefficient on that dummy variable got normalized to 0. So these coefficients here are interpreted with respect to the reference category that is not in the regression, and that is the first firm. So the way to interpret this coefficient is that there is something about this second firm that the log of scrap rates are 3.73 higher than the log scrap rates for the first firm. For the third firm, we have that the log scrap rates are 4.57 higher than the scrap rates for the first firm. And that's how these individual specific effects are actually interpreted. So again, the difference here is that these ones, the first one is normalized to 0. These ones are uh, and all of these are with respect to the first one that is normalized to be equal to 0. Whereas these individual specific effects here that came up after a within estimation here, they actually sum up to 0 as we show them here. So so there's a little bit of different relationship between them. Actually, if you look at, say, the second individual specific effect, if you do this individual specific effect plus this intercept here, that would be the firm specific intercept for the second firm. And by the way, that's going to be exactly the same number. Then if you sum up this coefficient here plus the intercept that we have here, it's going to be the same number. And what would also produce the same number is, say, for the third firm, if you are putting this number here for the third firm plus the individual plus the regression coefficient, the regression intercept here. So this number here, the individual specific effect for the third firm plus the regression intercept that we get from here, that would be equal to this this code that we have here, the individual specific effect for the third firm, plus the regression intercept here. And so this is by design. So again, that is the transformation here that we have of individual specific effects. Now, let's concentrate here on the R-square. And if I look at the R-square, this R-square is 0.92. If you recall, the previous R-square that we have here for the within is 0.22. So let's go ahead and actually calculate these uh, manually. So how we're going to do it, let's re-estimate the same model that we have here. And then let's display the model sum of squares, which is actually 7. And let's explain the residual sum of squared, which is 24. And how we calculate the sum R squared is the model sum of square divided by the model sum of square plus the residual sum of square. And this is how we get this 0.22. So this is basically the R squared for the within estimator. Now, how are we going to get the R squared here? If we re-estimate the dummy variables regression, and we're displaying the model sum of squared, which is 287, the residual sum of square is exactly the same. And if we use the same formula to calculate the R squared, here's how we actually replicate that this is 0.92. So what happened and why is the R squared so much higher in a dummy variables regression than the fixed effects within estimator? And the reason for that is that the residual sum of square is the same, but the model sum of square here is much higher at 287 versus what we have here at 7. The reason for that is that in the fixed effects within estimator, what we're doing is that these are actually not the original variables. These are the time d-mean variables. So each of the variables is the variable itself minus its mean over time. So when we demean these variables, we actually don't have that much variation that's left in the model, and there's just not that much to explain. On the other hand, the way you can also think about it is that if we put all of these dummy variables in this model, well, they really help explain the regression because we're saying there's something about the firm that makes the scrap rates higher or lower. Well, that would explain a lot, but it still doesn't tell you what exactly about that firm, right? Because these are unobserved effects in the individual specific effects. So it doesn't tell you exactly what about the firm, but it just tells you that there's something unobserved about this firm that makes log scrap rates higher or lower. And so that's why we would get very high R squared when we put fixed effects in there. But again, most all of that would be because we have these dummy variables as fixed effects. So now most, as I said, most tables that we produce of regression output for publications, they would not include these coefficients here. It would just say something at the bottom of this table that fixed effects are used. But usually we're not going to see all of these fixed effects for each of the individual firms. Like if there's a firm of a particular interest, we may go back and try to see what the individual specific effect is, but otherwise we would not be reporting these. Okay, so now let's talk about the random effects estimator. That's going to be the final estimator that we do here. And the random effects estimator, we would use an XT-reg. We would put the dependent variable in all the independent variables, comma, RE. That would be calling the random effects. And this is how the output is going to be looking like. So here we have, for random effects, again, well, this coefficient is actually significant at the 10% significance level. So here, basically, an increase in total number of hours in training would result in lower scrap rates, as the results are showing. Um, so here's the random, again, this is the random effects estimator. And after we estimate this model, we could actually recover the random effects parameter theta. So how we would do this is by just putting theta here at the end. And so if we put theta here in the end, this is what it's going to show. This will be this theta parameter, the random effects parameter. Well, how is it calculated? We can actually calculate it as 1 minus the square root, and we could be picking up the sigma squared for the idiosyncratic error term, and here divided by, again, the variance of the idiosyncratic error term plus 3. 3 is because we have 3 time periods, times the variance of the individual specific effect. That's what that would be. So this is again the formula that we discussed in the previous presentation. And if we display this parameter theta, this parameter theta would be exactly the same here as the median theta parameter that we have here. So looking at this theta, if we remember that if theta equals 1, we would be actually close to the fixed effects estimator. And if theta equals 0, we would be close to the pooled OLS estimator. So here we're seeing that we're actually much closer to the fixed effects or the within estimator as far as the results. So that's what this data is showing. Okay, so finally, let's talk about the Hausman test for fixed versus random effects. And the Hausman test is used to decide whether to use the fixed effects or the random effects. So here the null hypothesis would be that the fixed effects coefficients are not significantly different from the random effects coefficients, and the alternative hypothesis is that the fixed effects coefficients would be significantly different from the random effects coefficients. So in order to do that, let's go ahead and re-estimate the fixed effects and the random effects estimators again. So here we would be calling the fixed effects estimator, comma FE. So this is calling the XT dependent variable, all the independent variables, comma FE, calling the fixed effects estimator. And we would estimate store fixed. We would be storing these estimates. And then we would be doing the same for the random effects estimator. We would be calling xtreg and then comma RE for random effects, and we would be storing these random effects. And the way we would be doing this Hausman test is we will call Hausman, and then we would be calling these fixed and random uh, estimates, and we would be comparing. So here again, we're re-estimating the model, storing these coefficients, and then comparing them. So if you look at these coefficients, these are the coefficients that are actually the coefficients that are reported here. So this second model was the random effects, and these are exactly these coefficients. Okay. And so now the question is, I'm looking at how are these fixed effects coefficients different than the random effects coefficient. So if I'm looking at these coefficients, they're not identical, but they're very similar. These ones are a bit more different. These ones are a bit more different. These ones are kind of more different. And there's a bit more difference here. But basically, we want to know, are these essentially the same? Are they significantly different from each other or not? And so we would be taking, that's the difference between them, and we would be talking about the variance covariance, or the differences in the variance of these coefficients. And so we would be forming the Hausman test statistic. So the Hausman test statistic would be comparing these two coefficients here. So this is how the Hausman test statistic gets calculated. It's the difference in these coefficients that we see here for the fixed effects and the random effects. And then here we have the variance for the fixed effects minus the variance for the random effects to the -1 power. And then again, we have the fixed effects minus the random effects coefficients. This test statistic is 1.51, and the p-value for it is 0.91. This tells me that the coefficients are here not significantly different from each other. Well, um, so what this is telling me is that if the Hausman test statistic is insignificant, which is the case here, we need to use the random effects estimator because it's more efficient. So in this case, we're concluding that we would be using the random effects estimator. Why? Because these coefficients are similar in each other in value, so therefore they're both consistent. So that's why we need to move to the random effects so that we're more efficient. But if the Hausman test statistic was significant, this means if these coefficients were to be different from each other, then we have to use the fixed effects coefficient estimator because it's the only one, the fixed effects estimator, that would be consistent. So our first priority is to use a consistent estimator. So if the fixed effects and the random effects are giving you different results for the coefficients, significantly different coefficients, we would need to stick to the fixed effects estimator because it's going to be consistent. However, if both of them are similar coefficients and they're consistent, then we need to switch to the random effects estimator because it's efficient. So this is the conclusion here. So this is one of these rare cases where we found that the random effects is the preferred. And this is also showing the assumption that the individual specific effects are not correlated with the independent variables. Like typically we would find a lot of support for fixed effects in general. But anyway, we need to be using the Hausman test with our own specific data sets to first decide should we use the fixed or random effects, and then whichever one decision we came up to use the fixed effects or the random effects, we would be estimating only that model and reporting the results for the research paper. So this concludes this presentation. Thank you for watching.